The universe feels impossibly large because our rockets are painfully slow. Next-generation ion propulsion is about to change everything. This is not science fiction. It is an engineering reality taking shape in laboratories right now. The vastness of space has always been a problem of time as much as distance, and a revolutionary new engine is poised to collapse both for good. In this video, you will discover exactly how this gentle, continuous thrust could shrink our solar system, turning journeys that once took years into trips of mere months. We will uncover the physics that makes it possible and reveal the incredible missions already on the drawing board. What would you be willing to explore if the stars were suddenly much closer? That thunderous roar of a chemical rocket launch is a spectacular but fleeting burst of power. For a few short minutes, it fights against Earth's gravity with sheer brute force, a magnificent but wasteful effort. The real problem begins once the engines cut off and the spacecraft is left to coast. It is trapped by a simple, brutal law of physics known as the tyranny of the rocket equation. This is not a political rule but a mathematical one, a cage built from numbers. The equation reveals a cruel paradox. To increase your speed by just a little, you need to carry a lot more fuel. But that extra fuel has mass, making your entire spacecraft heavier. Now you need even more fuel just to push that extra fuel, which adds more mass, demanding yet more propellant. It becomes a self-defeating cycle where the vast majority of a rocket's launch weight is often just the fuel needed to lift more fuel. This is why a mission to a distant world like Jupiter requires a travel time measured in years. The spacecraft is given one powerful push at the beginning of its journey and then essentially drifts for the remainder of its voyage, a tiny speck on a vast, predetermined arc. Imagine trying to drive across a continent by flooring the gas pedal for 1 minute and then turning off the engine to coast the rest of the way. You would never make it up the next hill. This fundamental inefficiency is the invisible wall that has kept human exploration largely confined to our immediate cosmic neighborhood. Breaking this tyrannical cycle requires a completely different philosophy, one that trades explosive power for relentless patience. This gentle, continuous push is where the ion drive finds its power. At its core, the principle is elegantly simple, trading violent chemical fires for the quiet authority of electricity. It begins with a reservoir of a neutral gas, typically xenon. The engine first ionizes this gas, using electrical power to strip electrons away from their parent atoms. This process creates a soupy cloud of separate, positively charged particles, a state of matter known as plasma. Then comes the critical step. These newly freed ions are funneled into a region of incredibly powerful electric fields. Think of this as an electromagnetic accelerator, a kind of cannon that pushes on the ions with an irresistible force. They are shot out of the back of the engine at staggering velocities, often exceeding 100,000 miles per hour. While the physical push from any single ion is vanishingly small, the engine does not stop. It fires this focused beam of particles continuously for weeks, months, or even years. The difference in philosophy is like choosing between a sprinter and a marathon runner. A chemical rocket is all about that explosive, initial burst of speed. An ion drive is the ultimate endurance athlete, pacing itself with incredible efficiency, slowly and surely building up a speed that eventually eclipses its rival. This method of acceleration unlocks a new paradigm for space travel, one built on patience and precision. The journey of this concept from a speculative idea to a working machine is a story of persistence that began not in a spacecraft factory, but in the pages of science fiction and the notebooks of visionary engineers. Robert Goddard, the father of modern rocketry, first scribbled down the idea of an electric rocket in 1906. His theoretical musings were later echoed in the pages of science fiction, with authors like Arthur C. Clarke envisioning starships propelled by beams of light. For decades, this remained a captivating dream, an elegant solution trapped on paper. The first real leap from fiction to fact came in the 1960s, with small, experimental thrusters getting their first tentative test in the vacuum of space. They worked in principle, but they were not yet trusted with a major mission. The true turning point arrived with a spacecraft called Deep Space One, launched in 1998. Its primary goal was not just to explore an asteroid and a comet, but to prove that an ion engine could be the workhorse for an entire deep space journey. And it succeeded spectacularly, running its whisper-quiet engine for thousands of hours and fundamentally changing what mission planners thought was possible. This success paved the way for an even more ambitious traveler, the Dawn spacecraft. Dawn used its ion thrusters to perform a feat previously thought impossible for a single vehicle. It gently, patiently maneuvered itself into orbit not just around one, but two different worlds, the protoplanets Vesta and Ceres. This was not a fleeting flyby. It was a sustained, intimate study made possible by an engine that could nudge the spacecraft from one orbit to another with fuel efficiency that would be unthinkable for a chemical rocket. These missions transformed ion propulsion from a laboratory curiosity into a trusted tool, a technology that had earned its place in the deep space exploration toolkit. The quiet persistence of those early engines laid the foundation for the revolutionary designs being developed today. This staggering efficiency boils down to a single, crucial number known as specific impulse. Think of it as the ultimate measure of a rocket engine's fuel economy, its cosmic miles per gallon. A traditional chemical rocket, for all its thunderous power, has a relatively low specific impulse, typically around 300 to 450 seconds. It is a gas guzzler on an unimaginable scale, converting its immense fuel supply into a short, violent shove. Next-generation ion thrusters operate in an entirely different league, achieving specific impulse values between 5,000 and 10,000 seconds. This is not a minor improvement, it is a fundamental rewrite of the rules. It means that for every single kilogram of propellant an ion engine consumes, it generates a continuous, gentle push for an exponentially longer time. The engine wrings every last bit of momentum from its fuel supply. This incredible efficiency shatters the tyrannical constraints of the rocket equation. A spacecraft no longer needs to be mostly fuel tank. It can be smaller, lighter, and far more capable, with its mass dedicated to sensitive scientific instruments or spacious crew habitats for long voyages. This is the mathematical key that unlocks the entire solar system for human exploration, enabling missions to carry more and travel faster than we ever thought possible. But how do engineers achieve these almost magical numbers? The answer lies in pushing the very limits of physics, finding new and more powerful ways to create and accelerate those ions to even greater speeds. The quiet hum of an ion engine is about to get a serious upgrade. While the basic principle of using electric fields to hurl ions remains, the methods for doing so are undergoing a revolutionary transformation. The current vanguard of this technology is known as the Hall effect thruster. It represents a brilliant piece of engineering that replaces the physical grids of older designs with a clever magnetic trap. This magnetic field captures electrons, creating a powerful, invisible electric field that acts as an acceleration zone for ions. The result is an engine that is both simpler and more powerful than its predecessors, capable of generating a stronger push. You can already find these advanced thrusters operating on many commercial and government satellites, where they perform the vital, patient work of station keeping, nudging satellites back into their correct orbits for years on end with minimal fuel. But the frontier of research is already pushing far beyond this. The next wave of innovation is tackling the primary limitation of these engines, their lifespan. The superheated plasma that gives them power is also incredibly corrosive, slowly eating away at the thruster's internal components over thousands of hours of operation. The solution is advanced magnetic shielding, a kind of force field that contains the plasma without letting it touch the physical walls. This one improvement could extend an engine's life from years to decades, making it a truly permanent fixture on a spacecraft. Even more radical are concepts like electrodeless plasma thrusters. These designs eliminate physical contact with the plasma altogether, using different types of electromagnetic waves to create and control the thrust. Without material components being eroded by the searing plasma, such an engine could theoretically fire almost indefinitely. At the same time, researchers are rethinking the fuel itself. For decades, xenon gas has been the propellant of choice, but it is expensive and requires heavy, high-pressure tanks. Now, experiments are proving the viability of iodine, a cheap, solid material that can be stored compactly and vaporized into a plasma when needed. These might seem like small, incremental changes, but in the world of propulsion, they are absolutely crucial. Each one represents another step toward the ultimate goal, an engine that delivers the perfect balance of a meaningful push and seemingly endless endurance. This relentless refinement is what transforms a promising concept into a technology capable of carrying us to other worlds. The X3 nested channel Hall thruster stands as a physical testament to this progress, a machine that redefines what an ion engine can be. Developed through a collaboration between NASA and the University of Michigan, this is not a small satellite component. It is a behemoth designed for human exploration. In rigorous testing, it has shattered previous records for power, thrust, and operational current, pushing the boundaries of electric propulsion into a new regime. Its ingenious nested design features 3 concentric discharge channels working in harmony, a configuration that allows it to handle immensely higher power levels than a single-channel thruster of comparable physical size. This scalability is the key that transforms ion propulsion from a tool for robotic probes into the primary engine for a crewed spacecraft. The X3 is more than a prototype. It is a functioning blueprint for the engines that could carry the first astronauts to Mars, providing the gentle yet continuous thrust needed for a faster, more efficient transit. But unlocking this level of performance introduces a monumental new question, one that echoes the very limitations we faced with chemical rockets, just in a different form. Where will a spacecraft possibly get the immense amount of electrical power required to run such a powerful engine for months or even years on end? That insatiable demand for electricity is the final, critical piece of the puzzle. An ion drive's performance is directly chained to the power available to it. To generate a more meaningful thrust, you need to ionize more propellant and accelerate it even faster, a process that consumes a staggering amount of electrical energy. For missions close to the Sun, this problem has been solved with vast, wing-like solar arrays that unfurl to catch the abundant sunlight. But what happens when we venture further out, to the dim, cold realms of Jupiter and beyond, or when we need to power a massive crewed vessel with a powerful engine like the X3? In those deep spaces, sunlight is 1,000 times fainter, reducing those magnificent solar panels to little more than decorative ornaments. The only viable solution is to bring our own sun, a compact, self-contained power source utterly independent of our star's fading light. This is where advanced nuclear systems enter the story, not as weapons, but as life support for our ambitions. Projects like NASA Killer Power are pioneering compact fission reactors, rugged and simple machines designed to provide a steady, high-wattage stream of electricity for a decade or more. A single unit could generate the constant power of several large solar arrays, but from a package small enough to fit in the back of a truck. This marriage is the true catalyst, uniting a relentless nuclear heart with an incredibly efficient electric engine. It creates a vessel that is both powerful and patient, a ship that can accelerate for years on end without ever running out of energy. With this combination, the blueprints for our solar system begin to fundamentally redraw themselves. We are no longer limited to slow, coasting trajectories. We can plot continuous, spiraling paths through the void, building speed week after week until destinations that were once multi-year commitments drift into view within a single human season. A human mission to Mars, as currently envisioned, is a test of endurance as much as exploration. Astronauts would be sealed inside a capsule for a one-way transit of 6 to 9 months, a long and vulnerable coast through the void. During this time, they would face two invisible, relentless adversaries. The first is cosmic radiation, a constant drizzle of high-energy particles from deep space that steadily increases cancer risk with every day of exposure. The second is the physiological decay of microgravity, where bones lose density and muscles atrophy despite rigorous onboard exercise. This grueling profile is not an ideal. It is a compromise forced upon us by the limitations of chemical propulsion. But replace that single, powerful push with the gentle, continuous thrust of a next-generation ion drive, and the entire mission architecture transforms. The spacecraft would accelerate constantly for the first half of the journey, building speed day by day, and then gracefully flip around to decelerate for the second half. This constant acceleration profile could slash the transit time from nearly a year down to as little as 2 or 3 months. The benefits are profound. A shorter journey cuts the crew's total radiation dose by more than half and significantly reduces the health impacts of weightlessness. More importantly, the incredible fuel efficiency of the ion drive means the spacecraft is no longer mass-constrained. Mission planners could allocate that saved weight to a thicker, more robust radiation shelter, a larger and more comfortable living space, or additional supplies and redundancy systems. This transforms the mission from a bare-bones survival test into a far safer, more sustainable, and ultimately more productive voyage. It redefines a journey to Mars from a perilous expedition into a manageable commute. And if this new propulsion can make Mars a neighborhood, what does it do for the rest of our solar system? The same principles that collapse the travel time to the red planet can fling open the doors to the asteroid belt. The asteroid belt transforms from a distant field of flying mountains into a bustling celestial highway. A spacecraft powered by a next-generation ion drive would not be a mere visitor on a single, predetermined path. It becomes an agile explorer capable of a grand tour that visits multiple worlds in one mission. Think of it as a cosmic road trip where the vehicle can gently but persistently change its course, hopping from the dwarf planet Ceres to the massive protoplanet Vesta, and then onward to the enigmatic Pallas. Each of these bodies is a frozen time capsule from the solar system's birth, and with this new mobility, a single mission could study them all. The ion drive's gentle, continuous thrust allows for orbital changes that would be far too fuel-intensive for any chemical rocket, turning what was once an impassable expanse into a series of manageable destinations. This newfound access unlocks two parallel futures, one of profound discovery and one of practical enterprise. For scientists, it offers an unprecedented chance to read the solar system's original recipe by examining its preserved ingredients up close. They could investigate why these minor planets are so different from one another, uncovering clues about the forces that shaped our cosmic neighborhood. At the very same time, this capability is a total game-changer for the future of space commerce. Asteroid miners would no longer be limited to a single, lucky target. Their prospecting spacecraft could survey multiple asteroids, identifying the most promising sources of critical resources. They would be hunting for water ice, which can be split into hydrogen and oxygen for rocket fuel and life support, effectively turning asteroids into cosmic gas stations. They would also search for platinum group metals and other rare elements, materials that are essential for advanced electronics and are becoming increasingly scarce on Earth. This efficient mobility fundamentally rewires our relationship with these minor bodies, elevating them from distant curiosities to tangible assets that could fuel a true off-world economy. And as we master travel within this inner ring of solar system debris, our gaze is inevitably pulled further out toward the majestic giants waiting in the cold, dark depths beyond. Beyond the asteroid belt, the true scale of the solar system reveals itself. For missions to the gas giants, chemical propulsion forces a heartbreaking compromise. A spacecraft must spend years in transit, only to scream past its target in a fleeting, heart-stopping flyby, gathering all its data in a single, frantic pass. It is a glimpse, not a study, but with a nuclear-powered ion drive, that entire paradigm shatters. A vessel could make a direct journey to Jupiter in just a couple of years, and here is the revolutionary part: it would arrive with most of its propellant still in reserve. Instead of a momentary visitor, it becomes a permanent resident. This spacecraft could break into orbit around Jupiter itself, then use its gentle, continuous thrust to embark on a grand tour of the planet's fascinating moons. Picture an orbiter at Europa, the ice-shrouded world with a hidden global ocean. It would not be locked into a single, distant path. For months or even years, it could maneuver with precision, 1 week focusing its instruments on the cracked and chaotic terrain of the icy crust, searching for fresh deposits that might hint at recent activity. The next week, it could adjust its orbit to make detailed measurements of the subsurface ocean's depth and salinity, and then reposition itself to study how Europa plows through Jupiter's intense radiation belts, creating a complex magnetic fingerprint. This is not a hurried snapshot, it is an intimate, long-term conversation with another world. The same profound shift applies to Saturn's enigmatic moons. An ion-propelled spacecraft could orbit Enceladus, stationing itself near the towering plumes of water ice erupting from its south pole. It could repeatedly fly through these geysers, analyzing the complex organic molecules within without the desperation of a one-time chance. It could then travel to Titan, using its efficient engine to navigate the moon's thick atmosphere and map its methane lakes and rivers over multiple seasons. These engines transform our approach from reconnaissance to true exploration, allowing us to witness these alien environments as dynamic, changing systems. This newfound capability to stay and investigate does more than just satisfy scientific curiosity. It directly addresses one of humanity's most profound questions. Are we alone? By enabling sustained, detailed study of these oceanic worlds, ion propulsion gives us the tools to seriously and systematically search for signs of life beyond Earth. And if we can command such patience and power within our own solar system, what lies just beyond its edge? The incredible efficiency of these engines makes a previously unthinkable mission a tangible goal, a journey to the interstellar void itself. That final frontier, the space between the stars, is no longer an unattainable dream. While a voyage to another solar system is a challenge for future generations, next-generation ion drives are ready to build the bridge we need to reach its very edge. This bridge is an interstellar precursor mission, a spacecraft designed not for a star, but for the mysterious boundary of our sun's own influence. Imagine a vessel powered by a compact nuclear reactor and driven by powerful ion thrusters, accelerating outward with patient, relentless force. Its destination is the heliopause, the distant shore where the outward pressure of the solar wind finally yields to the pristine galactic environment. The legendary Voyager probes took nearly 4 decades to reach this frontier, coasting on momentum alone. A dedicated nuclear electric ship could make the same journey in a fraction of the time, perhaps just 15 to 20 years, arriving with its power and instruments fully operational. This is the critical difference. Instead of a dying whisper from a probe launched in the 1970s, we would receive a clear, strong voice from the edge of interstellar space, conducting the first ever in situ studies of the matter and energy between the stars. This spacecraft would do more than just cross a line. It would turn and look back, capturing an image of our entire heliosphere from the outside. For the first time, we would see the protective bubble our sun creates as it moves through the galaxy, understanding its true shape and structure. The data it gathers would be priceless, revealing how our local cosmic neighborhood interacts with the wider Milky Way. This mission is the essential proving ground, a shakedown cruise for the technologies and strategies that will one day carry a probe to a nearby star. It represents a tangible, achievable goal that stands squarely between interplanetary and interstellar travel. As we design ships capable of such incredible velocities, we inevitably confront one of space travel's most fascinating and counterintuitive obstacles. The faster you move through the cosmos, the less the conventional universe around you seems to cooperate. These fantastic speeds introduce a strange and beautiful quirk of the cosmos, a rule written into the fabric of space and time itself. As a vessel approaches a significant fraction of the speed of light, something extraordinary happens from the perspective of the crew on board. Distances to the stars ahead do not just feel shorter, they physically contract along the direction of travel. This is not an illusion, it is a direct prediction of Einstein's theory of relativity. At the same time, the astronauts' clocks would tick more slowly relative to those back on Earth. This phenomenon, known as time dilation, means that a journey to a star 10 light-years away, while taking a decade from Earth's perspective, could feel like only a handful of years for those on the ship. The universe itself is reshaped by velocity. While our next-generation ion drives will not approach these relativistic velocities, they are the crucial first step on a ladder that leads directly to them. They train us to think in a new way, to plan missions not from the static viewpoint of Earth, but from the dynamic reference frame of the ship itself. In this new perspective, distance is no longer a fixed number on a chart. It is a flexible quantity relative to your speed. This philosophical shift, understanding that the map of the universe changes with your velocity, is as profound as any engineering breakthrough. It redefines the very problem of interstellar travel from one of sheer distance to one of achievable speed and human endurance. And that second part, the challenge of endurance, presents its own monumental puzzle. How do you build a ship not just for a journey, but for a lifetime, possibly even for generations? The ultimate test for an ion drive is not a single moment of immense power, but the slow, relentless passage of time. These engines are designed to fire continuously for years, even decades, a duration that would reduce most complex machinery to a molten wreck. This marathon of operation places every component under immense, sustained stress. The most vulnerable parts are the electrodes and walls directly exposed to the superheated plasma. This ionized gas, the very source of thrust, is also a corrosive sandblaster on an atomic level. slowly but surely sputtering material away from the engine's interior. To overcome this, next-generation research is a deep dive into the world of advanced materials science. Engineers are developing new superalloys and specialized ceramics that can laugh in the face of this searing environment for tens of thousands of hours. But materials alone are not the only defense. The most elegant solution involves using the plasma's own nature against it. Techniques like advanced magnetic shielding are being perfected, creating invisible force fields that gently deflect the energetic ions away from the physical thruster walls. It is like building a magnetic moat around a castle, protecting the stone from any direct assault. This one innovation can reduce wear and tear by orders of magnitude, transforming an engine with a lifespan of years into one that could theoretically last for decades. Achieving this level of incredible reliability is not just an engineering goal, it is an absolute necessity. For a mission operating millions of miles from Earth, a single engine failure does not mean a disappointing end to data collection. It means the permanent, silent loss of $1 billion investment and years of human effort. This is why the quiet, relentless quest for a million-hour engine is one of the most critical endeavors in modern propulsion. Alongside this battle for durability, engineers must also master a task of exquisite finesse, managing the incredibly delicate control these engines provide. This constant, whisper-fine control redefines the very nature of navigation. Where a chemical rocket offers a series of jarring, all-or-nothing course corrections, an ion drive provides a smooth and endless ability to steer. It is the difference between steering a sailboat with a single, powerful gust of wind versus having a gentle, persistent breeze you can direct with your fingertips. This precision unlocks maneuvers that were once the realm of fantasy. A spacecraft can approach a small, tumbling asteroid and not just fly past it, but match its rotation and velocity so perfectly that they drift together through the void as if dancing. It can approach a moon like Europa and, instead of committing to a wide, looping orbit, use its thrust to hover persistently over a single, fascinating region, like a crack in the ice that might be venting ocean water into space. This allows for sustained, intimate observation that was previously impossible. These delicate operations require a brain as advanced as the engine itself. The spacecraft must be capable of autonomous navigation, constantly sensing its position and attitude, making microscopic adjustments to its thrust vector to counteract the subtle gravitational tugs from nearby bodies or the faint pressure of sunlight itself. It is a continuous, real-time recalibration, a silent conversation between the ship's computer and the forces of the cosmos. This transforms the voyage from a pre-plotted arrow shot into a living, responsive journey, a graceful orbital ballet where every movement is measured and intentional. This exquisite level of control is not just about reaching a destination. It is also the essential tool for managing a subtle but cumulative side effect of the engine's endless push. The spacecraft is not just expelling ions, it is also building up an electrical charge. Left unchecked, this static buildup could arc back to the spacecraft, potentially damaging sensitive electronics. The solution is a device of beautiful simplicity, a neutralizer that sprays a fine mist of electrons into the exhaust plume. This balances the ship's electrical books, ensuring the thrust remains clean and stable. It is a perfect example of the holistic engineering required, where every action, no matter how small, must be accounted for in the grand choreography of the journey. This slow, spiraling ascent is a quiet revolution in orbital mechanics. Picture a satellite already in low Earth orbit, not firing a single explosive thruster, but instead activating its ion drive with a faint blue tinge of exhaust. It does not race for the exit. Instead, it begins a patient, continuous push, like a swimmer making slow, steady strokes against a gentle current. With each completed loop around the planet, the spacecraft is just a little bit higher, its orbit imperceptibly wider. Week by week, this persistent spiral unfurls, a beautiful and deliberate unwinding from Earth's embrace. It may take months to finally achieve escape velocity, but the engine's gentle hum never stops working. The seeming slowness of this process is its greatest strength. Because the thrust is so low and so constant, the spacecraft is effectively fighting gravity across a vast distance rather than in one intense, concentrated battle at the beginning. This method uses energy with astonishing frugality. That radical efficiency translates directly into a profound economic shift at the launch pad. A spacecraft designed for this spiral escape does not need to be a giant fuel tank with a tiny payload on top. It can be launched on a much smaller, far less expensive rocket because the heavy lifting of escaping Earth is done by the persistent ion engine, not by the initial chemical booster. The launch vehicle only needs to deliver the ship to its starting orbit, a far less demanding and costly task. This patience at the outset is an investment that pays for the entire mission, freeing up mass and budget for more scientific instruments, more robust systems, or simply enabling more missions to fly. This economic advantage is what transforms deep space exploration from a series of rare flagship events into a sustainable, ongoing program of discovery. It is the key that unlocks the door not just to new destinations, but to a new era of access. That profound reduction in launch costs rewrites the entire business case for leaving Earth. The staggering price tag of sending a single kilogram to Mars, which currently runs into the hundreds of thousands of dollars, could plummet by an order of magnitude. Suddenly, the financial calculus for a mining company considering an asteroid water extraction venture shifts from impossible to plausible. For a university, launching a dedicated deep space telescope to study exoplanets is no longer a multi-generational dream, but a project that could be funded within a single research grant. This economic shift breaks the monopoly that only the largest national space agencies once held on interplanetary travel. We are moving from an era of flags and footprints to one of factories and foundries, where the primary goal is not just to visit but to stay and build. The most valuable commodity in this new economy will not be gold or diamonds, but something far more fundamental: water. Ice-rich asteroids become the strategic stepping stones of the solar system. Their water is a universal resource, easily split into hydrogen and oxygen, the very components of the most common chemical rocket propellants. An ion-propelled tug could slowly but surely ferry blocks of asteroid ice to a fuel depot in lunar orbit. This creates a network of cosmic gas stations, allowing other ships to refuel and continue their journeys without having to haul all their propellant from the deep gravity well of Earth. This self-sustaining logistics chain is the cornerstone of a true spacefaring civilization. The same principle applies to other resources, like helium-3 from the lunar soil, a potential fuel for future fusion reactors that could provide clean, abundant power back on Earth. As these economic pathways solidify, a new question emerges from the void. Who gets to make the rules in this new frontier, and how do we ensure that this great opening of the cosmic frontier benefits all of humanity, not just a select few? The blueprint for this new era of travel is being drafted not by one nation alone, but through a complex web of international partnership and commercial ambition. NASA and next-generation thrusters are being tested in collaboration with the European Space Agency, an organization that has already proven the worth of ion propulsion with its Smart 1 mission to the Moon and the ongoing Bepi Colombo journey to Mercury. These are not isolated experiments, they are complementary pieces of a larger puzzle. At the very same time, private enterprises like SpaceX and Blue Origin are pouring immense resources into their own electric propulsion systems, primarily for vast satellite constellations, but with a clear, long-term vision for deep space. This creates a fascinating duality, a landscape where agencies cooperate on foundational science while companies compete to drive down costs and increase launch frequency. The result is an unprecedented acceleration of innovation. This is not a Cold War-style race for a single, symbolic victory. It is a global sprint to establish the first sustainable and economically viable highway through the inner solar system. The entity that perfects the marriage of high-power electric thrusters with low-cost access to orbit will not just win a contract, it will effectively set the standards for how humanity operates beyond Earth for the next century. This immense power to shape our future inevitably leads us to a deeper question, one that transcends engineering and economics. What does it mean for our species to truly become multi-planetary, and what responsibilities come with this profound transition? This psychological transformation is the final and most profound effect of our new engines. A journey measured in months instead of years fundamentally rewires our perception of distance. Mars ceases to be a distant, reddish dot in the night sky and becomes a place you can actually travel to, a destination with a realistic travel time comparable to a long sea voyage in the age of sail. The solar system is no longer a collection of isolated points of light, but a continuous, navigable volume. This shift is critical because it changes the very stories we tell ourselves about who we are out there. An astronaut on a 9-month, one-way trip is a solitary pioneer, an individual facing an immense and hostile void with only a fragile shell for protection. Their story is one of survival against the odds, but an astronaut on a 3-month journey with regular cargo and crew rotations following similar timelines is not a pioneer in the same sense. They are a resident, a professional commuting to an off-world outpost. Their story is one of community, of building and maintaining a new branch of human civilization. This sense of being part of a connected, functioning network, even across millions of miles, is the bedrock of cultural resilience. It fosters the social and psychological stability needed for people to not just visit space, but to truly live there, to raise families and cultivate traditions under alien skies. This feeling of a shrunken, accessible cosmos makes the dream of a spacefaring species feel less like science fiction and more like an inevitable, tangible future. And with that expanded presence comes an immense and sobering weight of responsibility. This immense power to travel demands an equally profound sense of stewardship. The same gentle thrust that lets us orbit Europa for years also carries the risk of a silent, unintended invasion. Planetary protection, the discipline of preventing biological contamination, is no longer a secondary concern. It is a primary design requirement. An ion-propelled spacecraft designed to study the plumes of Enceladus or to land on the icy crust of Europa must be assembled in the cleanest rooms on Earth, with its components baked at extreme temperatures to annihilate any microbial stowaways. The goal is to ensure that the first life we discover on another world is not life we accidentally brought with us. This pristine preparation protects the scientific integrity of the search for life, but it also speaks to a deeper ethical duty to preserve these alien environments in their natural state. This responsibility extends from the biological to the geological. As we look toward mining asteroids for water and metals, we must ask difficult questions about our rights and our footprint. Does a company have the authority to completely dismantle a celestial body that may hold unique clues to the formation of our solar system? The act of extraction itself could alter an asteroid's spin or orbit, creating unpredictable consequences in a delicate orbital dance. The technology that makes these resources accessible also concentrates our impact, forcing us to confront the need for a new set of cosmic laws and sustainable practices. Our ability to reach these places must be guided by a wisdom that considers their intrinsic value, not just their utility. This careful, considered approach is the hallmark of a mature spacefaring civilization, one that looks beyond mere conquest toward a future of coexistence with the cosmos. And as we master the patience of ion propulsion, our gaze is already turning to the next leap, the engines that will harness forces far more fundamental to the fabric of reality itself. The gentle blue glow of an ion drive is a marvel of patience, but the human imagination is already racing ahead to engines that trade patience for pure, staggering speed. These are not replacements for the technology we have been discussing, but its direct descendants, concepts that build upon every lesson learned from managing plasma and enduring years of continuous operation. The next great leap could come from harnessing the same power that lights the stars, nuclear fusion. A practical fusion rocket would work by containing and igniting a superheated plasma, likely of deuterium and tritium, but instead of using that reaction to generate electricity, it would channel the furious expansion of the resulting helium nuclei directly out of a magnetic nozzle. The exhaust velocity from such a system would be a substantial fraction of the speed of light itself. Where an ion drive might push a crew to Mars in a few months, a fusion-powered vessel could make the same journey in a matter of weeks, completely transforming the physiological and psychological profile of interplanetary travel. This is not just a faster trip, it is a different kind of voyage entirely. Yet even fusion has a theoretical limit, a ceiling defined by the energy density of its fuel. To shatter that ceiling, we must contemplate the ultimate power source, the total conversion of matter into energy. This is the realm of antimatter propulsion. When a particle of matter meets its antimatter counterpart, they annihilate each other completely, converting their entire mass into pure energy according to Einstein's famous equation. The energy density is millions of times greater than nuclear fission or fusion. In theory, an antimatter engine could accelerate a spacecraft to true relativistic velocities, making journeys to nearby star systems a matter of decades instead of millennia. The challenges, of course, are monumental. Containing even a single gram of antimatter requires incredibly complex magnetic bottles, as contact with any normal matter would trigger a catastrophic release of energy. The production of antimatter itself is currently so infinitesimally small and expensive that it is measured particle by particle. For now, and for the foreseeable future, this remains a dream written in the mathematics of physics. Yet the steady, relentless progress in ion propulsion is the essential training ground for these future wonders. By mastering the long-duration containment of plasma in a Hall effect thruster, we are learning the magnetic confinement techniques that a fusion reactor will require. By perfecting the delicate balance of power and durability for a decade-long mission, we are building the engineering discipline necessary to one day handle the unimaginable energies of matter-antimatter annihilation. The ion drive is the foundational technology, the patient teacher preparing us for the day we finally graduate to the stars. This deep autonomy is the silent co-pilot on every long voyage. When a spacecraft is orbiting a world like Jupiter, a simple question sent back to Earth takes 45 minutes to arrive. The answer requires another 45 minutes to return. An emergency cannot wait for an hour and a half. This fundamental delay, imposed by the unbreakable speed of light, means that the vessel must be able to think for itself. It needs a form of artificial intelligence that goes far beyond a simple pre-programmed computer. This onboard AI becomes the ship's captain, navigator, and chief engineer, all rolled into one. It constantly monitors thousands of data points, from thruster performance and power levels to radiation exposure and hull temperature. It can detect a slight drop in power from a solar array and initiate a gentle roll of the spacecraft to reorient it for better sunlight, all without a single command from Earth. If a sensor fails, the AI can switch to a backup and then run a series of diagnostic tests to understand the root cause, perhaps even recalibrating other instruments to compensate for the lost data. This is not just automation, it is a form of machine resilience. The most fascinating application of this intelligence is in the pursuit of science itself. The AI can be trained to recognize serendipity. Imagine a probe studying the volcanic moon Io. Its primary mission might be to monitor a specific, known volcano. But if the AI's wide-angle cameras detect a new, unexpected plume erupting thousands of miles away, it can make a judgment call. It can temporarily reprioritize its observation schedule, slewing its most sensitive instruments toward the new event to capture precious data that would have been lost forever if it had rigidly stuck to its original plan. This transforms the mission from a pre-scripted checklist into an adaptive, curious exploration. The spacecraft becomes a true partner, capable of noticing the unusual and pursuing the unexpected on its own. This level of sophisticated decision-making relies on a digital brain that must be both powerful and incredibly reliable, hardened against cosmic radiation that can scramble conventional computer chips. The success of these incredible journeys will hinge on the seamless partnership between the patient, physical push of the Ion engine and the quick, intelligent mind of its artificial captain. This shared journey through the cosmos is more than just data collection. It is a cultural touchstone. When a spacecraft propelled by its silent Ion engine begins its patient spiral away from Earth, it carries with it the collective curiosity of our entire species. Live video streams from that vessel, showing our planet shrinking to a pale blue dot against the infinite black, do more than just document a mission. They forge a visceral, emotional connection for millions watching back home. High-definition tours of the asteroid belt, where every pockmarked rock tells a story billions of years old, are not merely scientific returns. They are epic narratives of discovery unfolding in real time. This direct access transforms abstract concepts of exploration into a tangible, shared adventure. It is this sense of shared adventure that ignites a spark in a child gazing up at the night sky. They are no longer just looking at stars, they are looking at destinations. The elegant physics of an ion drive becomes a gateway, inspiring that child to become the next physicist, aerospace engineer, or planetary scientist who will push the boundaries even further. This cycle of inspiration is the lifeblood of long-term exploration. Public enthusiasm generates the sustained political will and financial investment required for these decade-spanning projects, creating a virtuous cycle where today's wonder funds tomorrow's discovery. By making the cosmos feel accessible, we ensure that the universe we are so effectively shrinking remains an open, inviting, and endlessly exciting frontier for all of humanity, a shared experience that unites us under a common, starry ceiling. That gentle, continuous push of an ion beam is more than just a new way to move through space. It is a key unlocking our entire solar system for human exploration. We have traced its arc from the tyrannical constraints of the rocket equation to the promise of month-long voyages to Mars, from the bustling inner planets to the quiet frontiers of interstellar space. This is not a distant fantasy, It is an actionable blueprint for the future taking shape in test facilities and mission control centers today. It promises a cascade of scientific discoveries, from reading the original recipe of our solar system in the asteroids to searching for life in the hidden oceans of icy moons. It offers the foundation for a new economic sphere, built on the resources of those same asteroids and the fuel depots they will supply. Most profoundly, it enables a fundamental shift in our own story, transforming humanity from a species confined to a single world into one that lives and works across a network of many. The question is no longer if we will build this future, but how soon we will choose to begin. The engines are being tested, the missions are being drafted, and a shrunken, accessible universe is waiting for us to take the next